Hello everyone. So here for a given series RLC circuit, find out the transient response. So this is the given RLC circuit with the DC voltage 100 volts with the switches conditions T is equal to 0, resistance of 20 ohms, inductance of 0.05 and this capacitance of 20 microfarad. So first of all I am applying the switching condition. So when the switch is going to close means at T is equal to 0, so switch is on. So 100 volts is applied to this series RLC circuit. That voltage is developed across the resistor, inductor, capacitor. So the voltage across resistor is V is equal to I of t into R. Inductor is L into di by dt. Capacitor is 1 by C integral I of t dt. So voltage across resistor is I of t into R. Inductor is L into di of dt. Capacitance is 1 by C integral I of t dt. Simply apply the KVL equation to this figure B. So by applying KVL, this 100 volts is going to develop across your resistor I of t into R. This I of t into R value is 20 and inductor is 0.05 into di of t by dt and the capacitance is 1 by C integral I of t. So C value is 1 by 20 micro into integral I of t dt. So in this, make it as equation number 1. So in this equation we have the one differential term, one integral term. So simply apply the differentiation on both sides with respect to the time. So we know by the differentiation of this constant term we'll get a value as 0. Okay, so we'll write in the next step. So this differentiation of this constant 100 and differentiation of I of t with the value 20 plus 0.05. This is a double differentiation d square I of t by dt square plus 1 by 20 micro I of t dt. So in this one, this value is simply 0. So I am rewriting the terms like this: 20 into d I of t by dt plus 0.05 d square I of t by dt square. And by simplifying this, 1 by 20 micro will become 0.05 into 10 power plus 6, nothing but mega I of t. So in this one, so here we are getting a second order differential equation. So in this second order differential equation, I am taking this term 0.05 as constant. So by taking this term as constant, so we are getting the term d square I of t by dt square plus 20 by 0.5 into di of t by dt plus here again this term is again went to common na? So we have only the one term 10 power 6 I of t. So this term will goes to this as 0. So we are getting a second order differential equation as d square I of t by dt square plus 400 into di of t by dt plus 10 power 6 I of t is equal to 0. Make it as equation number 2. So this is we are getting a second order differential equation. So here we are getting a characteristic equation of d square plus 400d plus 10 power 6 of I of t is equal to 0. So the roots are, we will get two roots d1 and d2. So the roots are nothing but we know it is minus b plus or minus under root of b square minus 4ac by 2a. So here the value b as 400, a as 1, d as c as 10 power 6. So by simplifying it value, we are getting a d1 value as minus 200 plus 997 imaginary 0.7 j value. Similarly d2 as minus 200 minus 997.95 j. So here the roots are complex conjugates, so gives a underdamped response. So the solution is nothing but, so here we are getting the two roots. So d minus of k1 plus k2, again d minus of k1 minus k2 of I of t is equal to 0. And the solution is nothing but it has only the complementary function I of complementary function which is equal to e power of k1t into c1 cos k2t plus c2 sin k2t. So by simply substituting this k1 as minus 200, k2 as 997.95 j. So we are getting the complementary function e power minus 200 kt into c1 cos 997.95 t plus c2 sin 997.95 t. So make it as equation number 4. So in this equation number 4, again we don't know the constant values of this c1 and c2. So here c1 and c2 are constants. Then just simply apply the initial conditions at t is equal to 0 minus at t is equal to 0 plus. So and we know that the current across the inductor cannot change instantaneously. So simply just assume, to find out this constant, just assume that the current does not change instantaneously. So the current across in the inductor becomes 0. Simply substitute I is equal to 0 in these equations. At which conditions? Initial conditions na. So t value becomes 0. So e power 200 into 0 means this term becomes e power 0, nothing but value 1. Again c1 cos 0. So simply substitute t is equal to 0. Cos 0 value is nothing but 1. Again sin 0 0. So we are getting a equation 0 is equal to 1 into C1 into 1 plus C2 is equal to 0. Means from this one we are getting a term C1 is equal to 0. Simply substitute C1 is equal to 0 in this equation number 4. So we are getting a final equation I complementary function e power minus 200t into C2 sine 997.95t. Again in this equation also we don't know the term C2. So again to find out this C2, consider the voltage across inductor. We know that is L into di of t by dt. So at initial conditions it is equal to 100 volts. So simply substitute that value. So this is a constant value we know, L value we know. Simply take this value to this side. So you are getting 100 by 0.05. So you will get a 2000 value. And here from the equation 5 we know I of t is nothing but e power minus 200 into C2 cos 997 C2 sine 997.95t. Simply differentiate that equation. Because this is the equation number 5, complementary function is equal to e power minus 200t C2 sine 997.95. Simply differentiate that equation and make it to this 2000 value. So di of t is nothing but e power. Here we have the two terms e power minus 200t again cos t. Just to make the differentiation of that, so I am taking this e power minus 200t as a common term. Just I am differentiating this sine term. So it is e power minus 200t into C2. Sine differentiation is cos 997.95t with the coefficient 997.95. Again differentiate this e power minus 200t term. So you will get minus 200 into e power minus 200t with this term as a constant one. Okay. Again apply the initial conditions at t is equal to 0. This value is nothing but 2000 value. Simply substitute where t is there, simply substitute 0 here. So this value is 1, cos 0 is 1. Again sin 0 0 means this entire term becomes 0. So you are getting only the term di of t d is equal to 2000, which is equal to C2 cos 997.7. So here this value becomes 1, this value becomes 1. So you are getting that only terms 2000 is equal to C2 into 997.95. So from this term we are writing C2 is equal to 2000 by 997.95. So on an average this value is nothing but equal to 1000. Nothing but on an average we are getting a C2 value as 2. Simply substitute that C2 value in the equation number 5. So this is the equation number 5. E power minus 200 is C2 into sin 997.95. Simply substitute that value. C2 value is nothing but 2, 997.9. So the total response of the series RLC is nothing but e power minus 200t to 2 sin 997.95t amperes. This is the total response of the transient response of the series RLC circuit. Thank you.